The driven damped harmonic oscillator consists of a tuning fork, a drive coil, and a pickup coil. Notice how the drive coil and the pickup coil are located perpendicular to avoid crosstalk. We can slide the drive magnet down the tuning fork with a non-metallic object to verify that there is no crosstalk. The yellow trace is the drive signal, the blue trace is the pickup signal. Notice how the pickup signal disappears when I push the magnet out of the way. By sweeping the frequency of the function generator, I can find the resonant frequency of the tuning fork. I'm going in very fine increments of 1/100th of a hertz because it's such a sharp resonance. As I approach the resonance, notice how the phase shifts between the drive coil and the pickup coil. Right here I'm going through the resonant peak, and as I go beyond it, the phase continues to shift. If I go back down and try to find that resonance again, here's the peak and the phase shift, and notice how the pickup coil signal lags the drive signal. You can use the oscilloscope to make a rough measurement of the phase shift between the drive signal and the pickup signal. You know that there is 2 pi radians or 360 degrees between each peak, and you can count divisions on the oscilloscope to make that rough estimate. You can also use a Lissajous phase pattern to look at the phase difference between the 2 channels. Normally an oscilloscope plots magnitude versus time, but you can change it so that you're plotting one channel against the other. What you would expect for 2 signals that are in phase is a diagonal line with a positive slope. A diagonal line with a negative slope would give you 2 signals that are out of phase. So I'm going to sweep down in frequency, and you see that we're getting this diagonal line with a negative slope, which means they're out of phase. If I go back to the normal display, you see they're out of phase. If I sweep back up in frequency, we're getting closer to being in phase, but it never quite gets in phase, so we never get that perfect signal. You can see here they're just not quite in phase. The pickup signal is lagging the drive signal. I'm on the resonant frequency right now. If I cut off the signal going into the power amp suddenly, what you see is the pickup coil signal drops exponentially as you would expect. I turn it back on and it comes up exponentially as you would expect. If I go off by 1 hertz, I'm going to wait for a steady state, and I'm going to increase the vertical scale on the scope so we can see this better. Now what I'm going to do is I'm going to cut off the signal to the drive coil. Again, we get the exponential decay that we expect. But if I turn it on, now we don't get that exponential increase. We get a beat frequency. Let's try that for 2 hertz off of resonance and turn it on. And again, we see that beat frequency. I'm going to go down 3 hertz and now turn it on. Again, the beat frequency. How does that beat frequency relate to the drive frequency and the resonance of the tuning fork?